Okay, we've gone through our background information and sufficiently reviewed some of the aspects in spectroscopy that I wanted to. So now we're going to get specifically into rotational spectroscopy and vibrational spectroscopy. So with that, I'm going to have a couple learning goals on each of those two things. So the first thing we're going to talk about, we're going to get into the rotational spectroscopy. So we're going to review the different types of rotors and their energy solutions that we developed from our rotational quantum model, our rigid rotor model. Okay, so the first thing we need to consider is the moment of inertia. So a key molecular property in rotational spectroscopy is the moment of inertia. If a molecule does not have a moment of inertia, then it does not have a rotational spectrum. Okay, so there are several types of rotors, and they are classified based on their moments of inertia. And I say moments, plural, because we recognize that there will be more than one for complicated molecules. So that's why we really have to consider the sum of all of the different moments of inertia. So the first class of molecules to talk about is linear rotors. So good classic examples of these that we'll see spectra of are HCl or even carbon monoxide. We've used those as examples before. And in a linear rotor, there are two equal moments or two degenerate moments. And so those are given by the following, right? Assuming that my mass A and mass B are different, if I rotate around like so, that gives me a moment of inertia, or I could similarly rotate around the other way. So if I attempt to rotate around this way, that doesn't result in a moment of inertia. So we're really only worried about this molecule like tumbling over itself. Okay. So with symmetric rotors, good examples of these, as you might guess from the structure, would be like ammonia or even CH3Cl, so chloroform. So these will have two identical moments and one different moment. So we can see based on this picture right here, as it rotates around this way, that is often referred to as the I parallel, or it could rotate around this axis, or it could rotate around that axis. And we typically call those the perpendicular, I perpendicular. So now we'll talk about spherical rotors. So a good example, as you might guess, might be methane or even sulfur hexafluoride. And these will have three identical moments of inertia, right? So they will have moments all in the X, Y, and Z. And then finally, asymmetric rotors, a good example, I mean, that's the water molecule, right? So this will have three different moments of inertia in the three different axes. So the only ones that we're going to talk about here are spherical rotors and linear rotors, because we can use one moment of inertia to describe them. That's going to give us the easiest solution for now. So when we look at these, right, noting that we could break apart its solution based on the moments of inertia and the X, Y, and Z dimensions, which is what we did here, right? When I draw these crazy looking things, so those are the moments in the X, Y, and Z planes. So recalling then the solutions that we got, from the rigid rotor model, we could then, with noting that these are identical, just use the magnitude of the angular momentum vector. So now with that in mind, our energy solution, and we can do that with the linear rotor as well, just one magnitude of angular momentum, right? So recalling that picture here, when we have a center of mass, and of course then a mass rotating about that center, If it's rotating in this direction, right, remember your right-hand rule, our angular momentum is given by the j vector. Okay. So, and then recall the solution that we got from solving the rigid rotor model went as j times j plus 1 all over h bar squared, all divided by 2 times I. So this was our review of the rigid rotor model. So review rigid rotor, if you don't remember where this stuff came from, we're just going to use that solution directly. Okay, so I think I'm ready for the next video. Okay, I'll see you in the next one.